Hi everybody, I'm Giulio Passerotti and I recently did a pre-doctoral internship at the University of Melbourne, where I performed the analysis of the data obtained from the experiment that I'm going to present you. So, this study investigates how the properties of waves change as they propagate through a model of continuous sea ice. It's well known that Arctic sea ice is diminishing due to the climate change. An interesting consequence of this is the increasing fragmentation and variability of the marginalized zone, that is the area covered by broken flows between the open ocean and the continuous sea ice cover. This has led to the proliferation of explorations and exploitation in and around the region. Also, the navigation has intensified, as shorter trade routes like the northeast and northwest passages became navigable. In this context, reliable forecasts of meta-ocean and sea ice conditions are fundamental to reduce the risk associated to marine operation and safeguard the polar environment. Understanding the properties of the marginalized zone requires the analysis of the mutual interaction between waves and ice. In few words, waves penetrate deep into the ice-covered ocean and break up the ice cover into flows, while the ice field attenuates exponentially the wave energy over distance. In addition, waves introduce warm water and overwash the flows, thus accelerating ice melt and causing the flows collision. Experiments to investigate waves in ice processes have already been conducted, even though they have mostly been limited to wave attenuation as induced by plastic or wooden objects, with some exceptions represented by those experiments that used freshwater ice. Moreover, previous studies have always focused on regular waves, missing the assessment of the wave attenuation rate across the entire frequency domain. On the contrary, this study analyzes how the properties of irregular waves change as they propagate through a model of continuous sea ice that is scaled to be consistent with actual Arctic and Antarctic sea ice. The experiment was performed at the ice tank facility at Aalto University in Finland. So, at one end of the tank there is a computer-controlled wave maker. Then, to track the surface elevation, the tank was equipped with wave gauges in open water and pressure sensors below the ice cover. In addition, motion sensors were used to track the ice oscillation. Model ice was produced by spraying fine water mist, doped with a small quantity of ethanol, on the cool water surface. The ice properties were measured directly on the sheet with destructive cantilever beam tests, and were found to be consistent with properties of sea ice in the field. The wave maker was set with a low wave steepness, that is a usual wave condition in the Antarctic marginalized zone. The weak steepness is also important for the good realization of the experiment, because it guarantees the bending of model ice without breaking, minimizes the overwashed ice edge, and suppresses any nonlinear dynamics. Tests were first run in absence of the ice cover to evaluate the incident wave field, and then in the presence of the ice sheet to assess the spectral changes induced by the ice cover. The surface elevation was reconstructed from pressure sensors, and results to be comparable with the ice surface displacement, measured by the motion sensors. This figure shows a portion of the surface elevation time series, with the bottom series representing the incident wave field. As expected, energy attenuates with distance from the ice edge, with higher frequency components attenuating faster than the longer counterparts. So, the wave field becomes more narrow and there is the emergence of well-defined wave group structures. The time series at each probe were then used to compute the wave energy spectrum with a Fourier transform approach. These graphs show the significant wave heights and peak wave periods extracted from the final spectral shape. Both parameters are normalized by the incident counterpart in open water. In the upper panel, significant wave height decreases of about 30% after less than 2 wavelengths, and of 50% after 5 wavelengths. These results are consistent with attenuation of irregular waves observed in a smaller facility. The bottom panel shows the evolution of the peak wave period. As a consequence of wave attenuation, the dominant peak period increases compared to the incident value. It's important to mention that when the waves become longer, they tend to be less sensitive to the ice-induced attenuation. This explains the weak reduction of the significant wave height in the last pressure sensors. Here, a representation of the evolution of the full wave spectrum in ice, with the shaded area denoting the incident open water spectrum. The figure confirms that the energy attenuation is more remarkable at high frequencies. This results in a significant spectral downshift within only a few wavelengths of propagation in ice. Since the wave field is characterized by small amplitude, there is no nonlinear energy transfer, and all effects are only driven by linear dynamics. Attenuation rate is considered to be a function of the wave frequency only, and in mathematical models is described by an exponential function. For the present experiment, an overall attenuation rate is computed with a standard least square estimator, using all records from the 5 pressure sensors. The figure shows the attenuation as a function of the frequency, normalized by the peak frequency of the incident wave. The shaded area represents the 95% confidence intervals. The red dashed line represents a reference slope f³, since field measurements suggest that wave attenuation rates in sea ice are a function of f to the power of n, with n about 3. In the range 0.6–1.4 fp, where the energy content of the wave spectrum is higher, the experiment agrees with the f³ scaling. The relation is instead less strong away from this range, where more uncertainty is registered due to the low energy content of the wave spectrum. In conclusion, the experiment demonstrates that the attenuation of wave energy is important at a short distance from the ice edge and more effective at high frequencies. Moreover, it shows that attenuation rates follow a power law of the form f³, in agreement with field observations of sea ice in the Arctic and Antarctic. Another interesting result is the emergence of wave group structures with distance from the ice edge, again as observed in the recent missions in the Arctic. Thanks for watching.